In this demo, we present NeoSGG, a framework for the generation of a rich label property graph from video 7 streams in the semantic analysis. Our framework is divided into 3 parts: a scene graph generation pipeline, taking a video as input and extracting its visual content using deep learning models, a database module based on a graph data model and the NeoSGG DBMS to efficiently structure and store detections, and a querying interface to generate cipher queries to be sent to the graph database and provide a semantic analysis of the scenes thanks to graph projections. A more detailed overview of our framework shows the different steps of the pipeline and the graph data model. Our pipeline is thus composed of 5 steps as follows: keyframe extraction, to reduce the amount of data while preserving relevant information; object detection or instance segmentation, to spatially locate objects within keyframes; attribute recognition, to extract visual characteristics from person or objects; spatial semantic relationship detection; and object re-identification. Our graph data model is a labeled property graph. Each keyframe produces a spatial semantic layer. Detection and their attributes are stored in nodes and their respective properties. Spatial and semantic relationships then map the interaction between detection within graph layers. And finally, re-identification relationships enable the identification of all instances of the same detection between layers and their temporal connection. Now let's move on to the execution of our pipeline and the generation of the graph. Our pipeline module takes as input a video from the EDBT 2007 benchmark showing a man forgetting a suitcase on a train station platform. Here is an accelerated version of it. The total length of the normal version is 2 minutes and 16 seconds. Since the number of parameters is relatively large, we are using a config file like this one in order to modify them. For this example, we are using a simple subsampling method for the keyframe extraction, and we are using the smallest version of YOLO v5 for object detection. For each keyframe, we display the detections, the spatial and semantic relationships, and the re-identification relationship with previous layers in the form of dictionaries. As we can see, the total execution time is slightly longer than the duration of the video, which puts us in near real time. By switching to a faster GPU or to a cluster of GPUs to parallelize certain steps, we can fairly assume that we could achieve this goal. Now let's move on to the interface. It is opened by executing the following command. Here we essentially focus on the use case of lost luggage detection. However, our method is highly expressive and opens up a wide range of use cases such as violence detection, which we could illustrate in the demonstration. The different fields of the interface enable us to build a cipher query intuitively. For example, here we set the re-identification range up to 2. We select the predicates and also the object class, and then we can build the query like this. Then we can send it to the database and display the results. Here on the first window we can see the keyframes when the person is abandoning its bag or its suitcase. And on the second window we can see its corresponding ID and also the cropped image, and the cropped image of the suitcase and its corresponding ID. If I close it, I have 2 other windows showing a false positive since this person has no interaction with this bag, but the graph says it has some, and it is due to the detection pipeline. Finally, I wanted to show you what's inside the graph querying. In order to do that, I copy-pasted the query we just built into the Neo4j browser. What we are doing here is that we are looking for a specific pattern with a person linked to a bag, and we are looking if this person has a semantic link with the bag in the first layer, and also if the bounding box are being connected. And then we are recursively looking in the next layers if the same person, which has been re-identified, loses its semantic link with the same object which has also been re-identified, and also if the bounding boxes are being disconnected, that means that the person is leaving the object, and thus we are in the case of an abandoned luggage. Here we can see the execution with the first row being the true positive instance we just saw, and the second row being the false positive instance. And here above we can see a projection on the graph for the true positive instance with the 3 layers here. Thank you for your attention, and I hope to see you soon, maybe at the conference.